Welcome to week 7 of pre-calculus. This week we continue our conversation about exponential functions, and later on we will talk about logarithmic functions. So remember, last week we talked about the generic form of a logarithmic function, f at x equals a times b to the power x, where a is non-zero, b is strictly positive and different from 1. So today we will look at various transformations of these functions, and for the sake of simplicity, we will assume now that a is 1. Suppose now that a is 1, so we are simply looking at the function b to the power x, where again b is positive and different from 1. So let us summarize what we know about this function. Regardless of whether b is greater than 1 or in between 0 and 1, this function b to the power x is always injective. Remember, injective means that different values of the argument get mapped to different values of the function. From the fact that x1 is not the same as x2, it follows that b to the power x1 is not the same as b to the power x2. And indeed, when we look at the graphs of b to the power x for either b greater than 1 or b in between 0 and 1, we see that in the first case the function is monotone increasing, and in the latter case the function is monotone decreasing. Either way, it is injective. A function that is monotone increasing is, of course, injective. Regardless of b, this function is defined for every real number. And also, regardless of b, the image of this function is always the set of positive real numbers, whether it's increasing or decreasing. There is no x-intercept. That follows from the previous conclusion. F is always positive for all values x, so the graph will never intersect with the x-axis. This y-intercept at the point 0, 1. That is because b to the power 0 is 1. And here the same b to the power 0 is 1. Doesn't matter what b is. For any positive b, b to the power 0 is 1. Whether or not b is positive, whether or not b is greater than 1 or in between 0 and 1, determines whether f is increasing or decreasing. If b is greater than 1, the function is increasing, and if b is between 0 and 1, the function is decreasing. One thing I should mention here also is the horizontal asymptote. There is a horizontal asymptote y equals 0, and the reason for that is that the limit of b to the power x as x goes to, say, positive infinity is 0, provided that b is between 0 and 1. When b is between 0 and 1, the limit at positive infinity is 0, therefore y equals 0. The x-axis serves as a horizontal asymptote. And likewise, the limit at negative infinity of b to the power x is 0 in the case when b is greater than 1. We can see this in the graph. When b is greater than 1, limit at negative infinity is 0, and therefore the horizontal line y equals 0, which is the x-axis, is the horizontal asymptote. All right, these are the basic facts about the exponential function b to the power x, and now we look at various graph transformations of this function. In this first example, we look at three functions: 2 to the power x, which we know is simply an increasing exponential function, 2 to the power x plus 3, and 2 to the power x minus 3. As we know, adding a constant to a function corresponds to a vertical shift, and indeed, we see in the picture that the function 2 to the x plus 3 is obtained from the function 2 to the x by a vertical shift by 3 units. So instead of y-intercept at 1, we have the y-intercept at 4. 2 to the power x has y-intercept at 1. 2 to the power x plus 3, the red function, has y-intercept at 4. Of course, the vertical shift also shifts the horizontal asymptote. 2 to the power x has the horizontal asymptote at y equals 0. 2 to the power x plus 3 will have a horizontal asymptote at the line y equals 3. And likewise, the function 2 to the power x minus 3 is obtained from the graph of 2 to the power x by a vertical shift by 3 units downward. And so the y-intercept of this orange function 2 to the x minus 3 is at negative 2. And the horizontal asymptote is at negative 3. The horizontal asymptote of 2 to the power x goes downward by 3 units to produce the line y equals negative 3. All right, vertical shifts are easy. In this next example, we deal with the horizontal shift. We consider three functions: 2 to the power x, 2 to the power x plus 3, and 2 to the power x minus 3. Note that now we're adding 3 or subtracting 3 to x or from x, not to the function, right? As if we were to replace in the expression for 2 to the power x, if we replace x by x plus 3. As we know, this corresponds to a horizontal shift. And indeed, we see the graphs on the right. 2 to the power x is in blue. The function 2 to the power x minus 3 is obtained from the blue curve by a shift to the right by 3 units. And the red curve is the graph of the function 2 to the power x plus 3. It's obtained from the blue curve by a shift to the left by 3 units. These horizontal shifts certainly change the y-intercept. For example, the function 2 to the power x minus 3 will have its y-intercept at the point 0, 1, 8, not at the point 0, 1, where the blue curve has. And we can easily see that because the orange curve h computed at 0 will have the value 2 to the power 0 minus 3, which is 2 to the power negative 3, and that is 1/8. So indeed, 0 1/8 is the y-intercept for this orange curve. Unlike vertical shifts, horizontal shifts don't change the horizontal asymptote at 0. All three functions have the x-axis y equals 0 as their horizontal asymptote. And the y-intercept for the red curve, 2 to the power x plus 3 is 0.8. Again, that is easy to check if we compute g, which is the red curve, at 0. That's 2 to the power 0 plus 3, which is 2 to the power 3, which is 8. In both examples, all functions are still defined on the entire real line. So the theorem here at the bottom of the page simply summarizes all these findings. Suppose we have some constants c and d, and if we want to understand the graph of the function b to the power x plus c plus d, we can argue that the graph of this function can be easily obtained from the graph of the function b to the power x by a sequence of transformations. In fact, only two transformations are needed, and these could be performed in any order. Order doesn't matter in this case because we're not performing any stretches. You can, for instance, first shift vertically. You shift vertically by d units upward if d is positive, and if d is negative, you would shift by negative d units downward. Likewise, to account for the plus c term, you shift horizontally. If c is negative, like in this example, 2 to the power x minus 3, c equals negative 3, you would shift to the right by negative c units. And if c is positive, like in this example, x plus 3, you would shift to the left by c units. The y-intercept is at the point 0, b to the power c plus d. That's easy to see because f at 0 is simply b to the power 0 plus c plus d, which is, of course, b to the power c plus d. The horizontal asymptote becomes y equals d. Why is that? Well, if b is greater than 1, we can consider the limit of our function b to the power x plus c plus d at negative infinity. And now we clearly see that the first term, b to the power x plus c, approaches 0. That is because the power, the exponent, x plus c approaches negative infinity. C is a fixed number. X approaching negative infinity implies that x plus c also approaches negative infinity, and therefore b being greater than 1 means that b to the power x plus c base greater than 1 raised to the power negative infinity results in 0, and the entire limit equals d. If, however, b is between 0 and 1, we could consider the limit at positive infinity. And this time, because b is between 0 and 1, and because x goes to positive infinity, the exponent x plus c also goes to positive infinity. When you add c to a huge positive number, you still get a huge positive number. And raising a base that is between 0 and 1 to a huge positive power, of course, results in the value that is close to 0. Think about, for instance, raising 1/2 to the power a million. That is essentially 0. So this term, therefore, goes to 0, b to the power x plus c, and we again end up with limit d. Either way, the horizontal line y equals d is a horizontal asymptote. The fact that the horizontal asymptote is y equals d implies the next conclusion, that the range is d comma infinity, the interval d comma infinity. Why is that? Well, our function needs to be shifted horizontally and then raised or lowered according to d, then it's still an exponential function, so it's either increasing or decreasing. Either way, it will take all values from d up to infinity. Because b to the power x plus c will take all values from 0 to infinity, b to the power x plus c will take the entire interval 0 infinity. When you add d to this, you simply shift the interval 0 infinity by d to get the interval d infinity. And the domain remains unchanged. You can still substitute x by any number. The expression b to the power x plus c plus d still makes sense for any x. All right. Let's now look at stretches and compressions. Again, we have our function 2 to the power x, and look at two variations, 3 times 2 to the power x and 1/3 times 2 to the power x. As we know, multiplying a function by a fixed constant results in a vertical stretch or compression, and perhaps by a reflection about the x-axis if the factor by which you're multiplying is negative. So the graph of the function 3 times 2 to the power x is obtained from the graph of the function 2 to the power x by simply a stretch with a factor of 3. So you take the blue curve and stretch, and we multiply each y coordinate by 3. Likewise, if you want to obtain the graph of the function 1/3 times 2 to the power x from the graph of the function 2 to the power x, you need to compress by a factor of 3. So you take the blue curve, and then you divide each y coordinate by 3, meaning you compress by a factor of 3. This theorem at the end of the page summarizes all these conclusions. Suppose we're looking at the function 8 times b to the power x. It may be obtained from the parent function b to the power x by vertically stretching by a factor of a if a is greater than 1, like in this example, or by compressing by a factor 1 over a if a is between 0 and 1, like in this example. Here a is 1/3, and 1 over a is 1 over 1/3, which is 3. So we were compressing by a factor of 3. Either way, y-intercept is at the point 0a. That is again easy to see. F at 0 is a times b to the 0, which is a times 1, which is a. And also the horizontal asymptote stays at the x-axis. That is because, as we learned last week, the limit a times to the power b of x for b greater than 1 at negative infinity is 0, and for b between 0 and 1, this limit is 0 when x goes to positive infinity. That is immediately clear from the graphs. And remember that in this discussion, we agreed that a is positive. Now, if a is negative, all we need to add is a reflection about the x-axis. For example, say we have again the graph of 2 to the power x. The graph of negative 1 times 2 to the power x is obtained from the graph of 2 to the power x by a reflection about the x-axis. Remember, placing a minus in front of the function has the effect of reflecting about the x-axis. Now, if we replace x in the expression for our function f by negative x, that has the effect of reflecting about the vertical axis. So the graph of 2 to the power negative x will be symmetric about the vertical y-axis to the graph of 2 to the power x. And it's worth noting, by the way, that 2 to the power negative x is simply 1/2 to the power x. So the theorem here summarizes reflections. To graph negative b to the power x, all we need to do is reflect about the x-axis. So the x-intercept still is changes, of course, from the point 0, 1 to the point 0, -1, which is symmetric to the point 0, 1 about the x-axis. It will now have the range or the image from 0 and downward, so from -infinity up to 0. The asymptote at 0 still stays, and the domain, of course, stays the same. All that you can see in the graph on the left. 2 to the power x versus -2 to the power x. And for the function b to the power -x, which is obtained from the function b to the x by replacing x by -x, we perform a reflection about the vertical axis. That naturally doesn't change the y-intercept, it's still at the point 0, 1. Doesn't change the horizontal asymptote, it's still y equals 0. Doesn't change the range. It's still from 0 to infinity. Doesn't change the domain. It's still the entire real line, so the question is what changes? Of course, what changes is the monotonicity. 2 to the power x was monotone increasing, 2 to the power -x is monotone decreasing. And the last theorem here summarizes all of these transformations. Suppose we have a function of the form a times b to the power x plus c plus d. Here the base b, as always, is positive, different from 1. And a, c, and d are constants. We certainly need a to be non-zero. And the question we want to answer is how the graph of this function is related to the graph of the function b to the power x. Well, I would first perform a horizontal shift. We perform a horizontal shift by absolute value of c units. If absolute value of c, if c is positive, absolute value of c is simply c, and we shift to the left. And if c is negative, absolute value of c is -c. So -c will be positive then. And we shift to the right by this many units. We then perform a vertical stretch or compression, depending on whether a by absolute value is greater than 1 or between 0 and 1. If it's greater than 1 by absolute value, it's going to be a stretch by a factor of absolute value of a. Or if it's between 0 and 1, it'll be a compression with a factor of 1 over absolute value of a. Additionally, if a is negative, we need to perform a reflection about the x-axis. So flip about the x-axis. And then lastly, we need to shift vertically by d units. If d is positive, we're shifting upward. If d is negative, we're shifting downward. And in this last example, we need to write down the equation for the function described below. It's a function e to the power x. Remember, e is the special base, roughly 2 to the power 7, 1, 8 to 8. In particular, it's greater than 1. And this function we stretch by a factor of 2, reflect across the y-axis, and then shift up by 4 units. Well, if we do this step by step, e to the power x looks like a typical increasing exponential function, passing through the point 0, 1. If we first vertically stretch it by a factor of 2, we multiply each y coordinate by 2. So we get an increasing exponential function with y-intercept 0, 2. Next, if we reflect, by the way, this is e to the power x, this is e to the power x times 2. Now we reflect across the y-axis. That will result in the exponential function which is decreasing and passes through the point 0, 2. The reflection about the y-axis corresponds to replacing x by negative x. So that function is y equals 2 times e to the power negative x. And finally, a shift upward by 4 units corresponds to adding the 4. So if we draw the line y equals 4, I should take my last function and shift it upward by 4 units. So the y-intercept will now be at the point 0, 6. And the function will look like this. Let's call it g, for instance. The domain of g is, of course, the entire real line. And the image of g will be all numbers that are strictly greater than 4. And note again that this function is decreasing. All right, this is it for exponential function. Our next topic will be logarithmic functions. Thank you.